record on this computer, and now we should be ready to go. Okay, good. So good afternoon, everybody again. Welcome to the third lecture of deep learning for NLP. Today we have super equipment, so everybody can hear me better than usual. And I'm still recording on Zoom as well. So we just start with, so thanks for the feedback, by the way. And here's a couple of things I want to address. So microphone, okay, so that's solved. If it's better, I'm glad to hear that. Some people ask what was the connection of last lecture to NLP at all. And I have to admit, I didn't make it clear enough, but today it will be really clear why are we actually interested in minimizing functions and all these mathematical things. Okay, so let me just address this today. Apologies. Some people ask me for whether I can stream the thing like during actual recording and live, whether I could stream it on Zoom. And the answer is not really. I'm sorry, because it's getting too complicated. It's like streaming, recording, this microphone, that microphone, and all these presentations. So if you can't really see what's on the screen, open up your slides and you'll follow. That should be fine, but I'm not planning to stream that. And I don't think the internet actually could work like for streaming here through Edroom. I'm not sure. So sorry about it. Some people are actually thought that lecture 2 was either too boring or too hard. And it's it's interesting because that's the point. I mean, we have really like diverse background here. And what's the required background knowledge? And I can't really tell. I mean, we need some little bit of programming, little bit of mathematicals, not be scared of math, but what exactly it means, like which courses and so on, it's hard to tell. So we have really a mixture of different backgrounds. What I'm trying to is to have everyone on board, like really trying to get you on board, even though you didn't study computer science or you didn't study like deep learning before, or machine learning and stuff like that. So, so sorry. I mean, you have to be selective as well. And if it's boring, you can leave. That's fine. You cannot skip it here live because it's not YouTube. On YouTube, you can skip it. Okay, good. So there is one point about the live questions. I'm asking you whether we could have like an app and maybe do like online questions and you can address it on the phone. It would be awesome. I would love to do that. I would love to have all these questions, but I don't know. I mean, it's getting, again, a little bit complicated. Like technically, it takes quite a time. So what I want to say, if you have any questions, if you feel shy to ask, there's nothing like a stupid question. Like ask whatever you want to ask and don't hesitate. It's fine, right? Because as I said, like people have different backgrounds and different kind of prerequisites and knowledge. So feel free to ask anything. I will leave more time maybe on some detailed things that you can think about it, but the app live questions is something I considered, but for technical reasons and a lot of preparation time, I haven't really integrated it yet. Maybe something to do in the future. Okay, but otherwise, I really appreciate your feedback. So I had like 12 responses, which is great. I would love to have 100, but maybe next time. Great. So what are we going to do again? The title of this lecture. Oh, let me just get rid of this ugly thing here. Get away. Hi, get away. Well, doesn't matter. So what are we going to talk about today is the binary text classification, right? And now we're getting finally into NLP. And what we were trying to achieve today is that, well, we're going to work with this super easy, well, to some extent, easy example task, which is binary sentiment classification into positive and negative. And if you remember from the first lecture, when we showed a couple of tasks in NLP, there was this IMDb data set. So this is an example of binary classification. You take a movie and predict whether it's positive or negative, right? And we have these reviews, which are either short or long. And today we're going to learn quite a simple but still powerful supervised machine learning model, which we also know as logistic regression or maximum entropy classifier. But in fact, it's already a sort of single layer neural network. So this, we're building up from scratch really to deep learning and NLP and all the architectures which are coming step by step. So this means this is an essential and important building block of deep neural neural networks. Okay, this is what we're going to address today. There's one premium spot here in the first row, if you're not afraid. Well, you will see everything then. And if you sleep here, that's fine as well. We had somebody slept here last time, and that's fine. No, I mean, it's after lunch. Come on. I mean, you know, the Mensa food is not good, but still food, so it makes your brain kind of, yeah. So, okay, but before we jump into this task, so binary classification of movie reviews, what are the actual challenges of natural language processing? And we should actually talk about them. We haven't talked about the challenges. Why NLP is different from, I don't know, like computer vision. So there is one thing, which is ambiguity and variability of human language. So language is highly ambiguous. If you look at this example and compare, I ate pizza with friends and I ate pizza with olives, they look the same on the surface, but in very different things. So there's some ambiguity here. This is syntactic ambiguity, right? So you cannot just replace one with the other and they are similar. Not at all. They mean totally different things. Language is highly variable because the core message of I ate pizza with friends can be expressed as, well, friends and I shared some pizza, or the pizza was eaten by myself and my friends and so on. So there are so many ways to say the same thing. So this is the high variability. And we as humans, we are great users of language, but we are kind of poor at formally understanding and describing the rules that govern language. You know, linguistic is kind of the science of trying to do so. But, you know, this is a hard task. But we use language like very freely, and we understand it. So what shall we do about it? Well, we have supervised machine learning, which is going to save us for natural language processing. Because the best known set of methods for dealing with language data so far is something along supervised machine learning algorithms. So the supervised machine learning algorithms, they're trying to learn patterns and regularities from a set of pre-annotated input-output pairs. So we have some pre-annotated, maybe by humans, maybe just by scraping from the internet. We have some data and input-output. So what input-output will be for the sentiment classification on IMDb? What's the input? What is the input for us here for the sentiment classification? It's a text, yes, and the output would be yes or no, yeah, or maybe positive or negative, exactly. Input output, and we have plenty of them, and we use machine learning to try to build such algorithms. Which means that machine learning excels problems where a good set of rules, so we can kind of hard code it, like saying if there is a word such and so on, but it won't scale for this domain. Because annotating the expected output for a given input is relatively simple. So you read your review and you say like, yeah, it's positive. Sure, okay, positive. So it's easy to create data, training data, and hard to write rules. So this is where machine learning will help us. But language is actually even more challenging. So it's not like everything is shiny and nice, because natural language has properties that make it even more challenging for machine learning. And there are 3 points about language which are hard. So language is discrete, compositional, and sparse. And we're going to address each of them in detail. So language is symbolic and discrete because we have the basic elements of written language, which are, what is it, characters, yeah. And the characters form words that denote objects or concepts, events, actions, and ideas, and many other things. But these are discrete symbols, which means that words such as hamburger or pizza, you know, they each evoke in us sort of like a mental representation. If I tell you pizza, it does something in your brain, and you see maybe the pizza. If I tell you Mensa food, it evokes certain thing in your brain as well. But these are distinct symbols, right? Whose meaning is external to them, so they don't carry any meaning. The meaning is interpreted in our heads. There's no inherent meaning in these words. And there's also no inherent relation between the hamburger and pizza, which can be inferred from the symbols or letter themselves, right? I mean, hamburger is just a couple of letters and pizza is a couple of letters. But looking at the letters, you can't do anything about it. You can't say they're similar, right? If you change one letter, you get something similar to pizza. but it won't be that pizza. It doesn't work. It's just two discrete symbols, completely, independent in their form, which in there are written. So if you compare this to, let's say, something like color in machine vision or acoustic signals, these are continuous, right? So you can use like a simple mathematical operation to convert a colorful, like full color image into grayscale, right? And you can compare two colors based on their properties, such as hue and intensity. So these are continuous, and they carry the meaning by themselves. And you can just run function on them to create something something similar or something new you can compare. This can be done with words, because there is no simple operation to move from the word, for example, red to the word pink, right? I mean, you can move from pink to red let's say computer vision, or by in graphics, by manipulating the values of these pixels. You can do that objectively, basically. But here in language, from red to pink, you just need to know, and you have to look up it in a dictionary and stuff like that. So this is like what makes language a bit different. This is the discreteness. Okay. Any questions so far? Everybody's with me that this is more complicated than we think, like how to get from red to pink, because these are just two different things. Okay, great. Then the second part was that language is compositional, because we compose letters to words, to phrases, to sentences. And the meaning of the phrase can be larger than the meaning of the individual words, and they kind of follow some intricate rules. Examples, we know all of them, like multi-word expressions. New York are two words, but their meaning is maybe more than just New and York together. Or look something up, phrasal words, look up. Look something up is something different than look something and up. It's just different meaning, right? Idioms, even worse. Kick the bucket. Who knows what kick the bucket is? To die, yeah. But to die is different meaning than composition of word to kick the bucket. Like if you don't understand the idiom and just literally translate a thing, like kick the bucket, why? Makes any sense? But composition makes a different sense. Or blue chip. Who knows what's a blue chip? It relates to stocks, but not yet. This is like stocks which are kind of safe to invest in. Yeah, like the winner, like today's, I don't know, Google maybe, blue chip. Yeah, but it's not. If you know what blue and chip is, it doesn't tell you anything what a blue chip is together. It's like a different meaning. So this is the composition. So to interpret the text, we need to work beyond the level of letters and words and look for sequences of words, such as sentences or even the complete documents. And we as humans, we do that. We understand this compositionality. For machines, it's kind of tricky, right? And the last one is data sparseness, because the combinations of words to form meanings goes basically to infinity. So there's so many ways you can say so many things. And we could never, ever enumerate all possible valid sentences, for instance. I mean, there's basically infinite amount of possible sentences. Morphological language, the way you build words, almost infinity. So there's no clear way of generalizing from, for example, from one sentence to another, or even like defining the similarity between sentences that doesn't depend on their meaning, and the meaning is unobserved, right? So the meaning is somehow you have to interpret the meaning, and then you can say whether sentence A is similar to sentence B. But looking at just plain characters, well, it doesn't tell you like their similarity. Maybe flipping words and stuff like that, but it's just a proxy. It's not like a true similarity. So, and the point here with the sparseness is like, even if you have like a huge example set, we are very likely to observe events that never occurred in the example set, and that are very different. So the number of combinations you will see in training data, it's just never exhaustive enough to see everything. And most of the time when you train a model, so in the next year, you will see there's new words, personal nouns, for example. Models trained before COVID-19 were completely useless when COVID-19 hit for like Twitter sentiment prediction, for example, or trend prediction, because there was a new word which was everywhere, but nobody knew the word before COVID-19. So all language evolves. and is sparse. Okay, so these are the three kind of like biggest challenges. What makes language a little bit hard? Any questions to that? Or any other personal experiences why language is hard? Whoever worked with language already? Great. Okay, so let's move on. We have the scene set up. Now we want to move to supervised machine learning on text data. And now we're getting back a little bit to mathematical notation because we're going to use some functions. So, okay, so we're going to use scalars, vectors, matrices. Now here I kind of assume you know a little bit of linear algebra. So you know what a vector is, and you know how to multiply, or matrix is, and you know how to multiply vector and matrices together, okay? If this is not the case, look it up. It shouldn't be rocket science, but you just need to, you know, practice a little bit, all these things. So what we're going to use is lowercase letter for scalars. So scalar is just a number, you know, 1, 2, pi, and so on. We're going to use lowercase bold letters for representing vectors, right? So these, can you see the difference here in the slides? I guess so, right? So these are vectors, these are scalars. And we're going to use bold uppercase letters for matrices. So these two are matrices. So matrices is basically two-dimensional arrays. And well, this is how we decided to do this for, you know, for this lecture. And you will see many different ways of how to write a scalar, a vector of matrix. So maybe in physics, you would see maybe something like this would be a vector, or many other things. So this is always like context dependent. So we're going to use this kind of sort of notation. And so, you know, vectors have elements in there, and we're going to use this this parenthesis and the index operator of vectors of matrix. That, for example, bi here in the, you know, in this index operator is the ith element of vector b, right? And the same for indexing matrices. We're gonna have I and j will be like the ith row and j column of matrix w. So this should be standard. Yes. If there will be any task like you should write vectors in the exam, I'll make it either explicit or I just will accept like a common sense thing, right? Yeah, how I mean, if you can draw the difference on the exam between lowercase bold and lowercase non-bold, good for you. I mean, I'll be super happy, right? The thing which I see on exams is like people really can't even write in capital letters, even like explicitly ask, right? So I'm asking for you. So exam, okay. You can practice for exam the only thing which really matters for the exam, learn how to write in Comic Sans. Because otherwise we can't read it. I'm sorry, you know, and I put it on the first page, write in Comic Sans, please, or something like capital. So you can use anything you want then. I mean, we'll be explicit about it. Because this is like, you know, this is a context dependent where you are. Yeah. Any other question to the notation so far? Yes. Second? Oh, 0 index or 1 index. I don't think we care actually here. I mean, I think we're gonna use like 1 index. Yeah, 1, like mathematical is from 1. Yeah, that's a good point. But typically we don't really care because we're multiplying them together, and then it doesn't matter if you start from 0 or from 1. Okay. Any other questions so far? Okay, let's move on. So then we're gonna have a sequences of vectors where we use also like the use the index, but not in the parentheses, but just like that. So x1 period n will a sequence of vectors x1, x2, and so on, so on. It's basically an array of vectors, or it's a set of vectors. And we might be concatenating vectors together, which will be denoted like that. So v1, v2, and this is where you take one vector and add another, you know, at the end of the other, and you end up with the other vector. Yes, a question here. So, and the next stop is going to be, we're gonna use row vectors. That's a great question. Great timing. I mean, if you read that before, if you didn't read it before, this is great timing. Where were you sitting last time here? So you're the guy who always, you know, it's like 5 seconds before and asking the question is coming. Yeah, I remember you. This is cool. Okay. It looks like we practiced that, right? So like this bridge to the next topic. So there's so many notations, but we're gonna use, and maybe a little bit like unorthodox, we're gonna use row vectors. So vector is basically a list. So here's an example of dimension 5, and this is our vector. So it's a row vector, which is simply a list or 1D array of numbers. Typically in mathematics, you will see like vector is a column vector. No, 1, 2, 3, 4, 5, and in a text you would write x as 1, 2, 3 transpose. This would be like on a line. We're gonna save this effort and we're gonna just pretend these are just row vectors. Okay, so this is a decision, a design choice we're using. Okay, what's the concatenation versus two vectors? So in the concatenation, let me just delete that. No. It's basically saying if you have like vector, so x1 is 1, 2, 3, and x2 is 4 and 5, then their concatenation x1, x2 is going to be just one vector, 1, 2, 3, 4, 5. We just take them after one each other. Yeah, okay, cool. Any other question to the notation? Great. So multiplication example here. Yes. Okay. So we're going to be multiplying vectors and matrices. And here's an example. So we have a vector of dimension d in. It has some meaning, which will be clear later, but it has some dimension. Then we have a matrix W, which is also d in times d out, so two-dimensional matrix basically. And we have vector B of dimension d out. And we're gonna compute the output y, which is this equation. So what we're gonna do is we multiply the vector by matrix and add another vector. Okay, so here the example is that for these actual numbers, like dimension in is 3 and dimension out is 2, means that we're gonna take this vector x, which is 3-dimensional, multiply by 3 times 2 matrix, which gives us what? What will be the output of this computation? What will be the dimension? We multiply vector by this matrix. So 3 vector times 3 times 2 matrix. What's gonna be the result? Yeah.
Like a vector of 2 elements?
It's gonna be a vector of 2 elements, exactly. It's gonna be vector of 2 elements, exactly. And then we're gonna add it to this vector, and we can add 2 vectors together if they have same dimensionality, and we end up with this 2-dimensional vector. Why I'm using the in and the out, as you see here, so the in will be the input here, so the input dimension, which will multiply by this matrix to the output dimension, which is here 2, right? This is the output of the multiplication, and then we're just summing our vectors to get this. Any question to this, what we are doing? Because typically you can have multiplication of matrices the other way around. So you can also write x is the W, the matrix, times x plus b. And I think like in mathematics, you actually write this, like you start multiplying first matrix by vector, which is also fine, but then you have to pay attention to these two dimensions, whether it's a row vector and column vector. And we're using this kind of little bit unorthodox thing, because this is typically this is coming in. So this is a vector coming in, then you have the matrix, which has so in times out, and out, and you end up with the out dimension, right? Yes, question.
Three columns and 2 rows for the matrix to be able to multiply with x.
Yes, is it correct? 3 rows and 2, because you take, how do you multiply vector by matrix? This one with this one, plus this one with this one, plus this one with this one will give you the first. Then you go this one times this one plus this time times this one plus this one times this one will give you the second one.
Okay. I don't know. I was always like looking at the columns as vectors and multiplying the first element of X with like those vector.
Okay. Yeah. So I'm almost sure that this is correct, like 99% sure this is correct multiplication of a vector by matrix. And you might have different kind of internal representation of multiplication of matrices and vectors, which is fine, but this has a meaning actually. You have a vector, okay, this is an interesting point. So you have a vector and multiply by a matrix. What are you doing? What is it? You have a vector, which might be a vector. Oh, sorry, yeah, it might be. Let me just reiterate, which might be a vector in a space, and you multiply by a matrix. What is it? Sorry, you were first, like behind you. Okay, yes. So you first. It's a linear transformation. Yes, it's a. Well, in a way, yeah, but yeah, it is. So there's some weighted sum, exactly, because you do linear weighting, so it's the same thing, right? It's a linear transformation, right? What does it mean? What is a linear transformation? Exactly. It's a projection. You're projecting from one space to another space. This is the core of linear algebra, basically. So there's some basis in there, and so you can go really wild about it. But basically here, we have this vector, and by multiplying by this matrix, we're projecting this from 3 dimensions into 2 dimensions. What could be a projection of 3 dimensions into 2 dimensions? What is it? If this is linear? Yeah, like a computer game, exactly. You just put like 3D world into two dimensions. How do you do that? By projecting through a matrix. Nothing more. And also it's a linear transformation, so it's a linear map. So there's some properties that's kind of like the distances are kind of preserved and scaled and stuff like that. So that's why we're doing this. Like we're taking this is input vector, I want some output vector, so I'm multiplying by a projection matrix, and then something comes out. Okay, great. Any questions to that? Sounds perfect. So let's move on, because we might have even, yeah, okay, there's one. We can simplify things. So here we are gonna have the output dimension is gonna be of dimension 1. So we want to produce a scalar, right? So now the input vector is still the same. So we have 3-dimensional vector and multiply by 3 times 1 matrix, which gives us what? So this times this gives us a scalar, yes, which we then add to another scalar and get a scalar out of it, right? And we can kind of make it easier, because this is a very nested matrix, like 3 times 1, oh, that's ugly. So we kind of use the dot product here instead and transform this matrix into a row vector. So this will become basically this. And here we have 2 row vectors, and this operation is the dot product. It's basically taking each element, multiplying together and summing up, right? So the dot product of 2 vectors is you iterate over all elements and just multiply the values at the positions. So everybody knows the dot product. If not, then look it up, but there's nothing complicated about it. So here we say, yeah, okay, let's make a dot product and to get a scalar, and then there's a scalar. So these 2 things are equivalent, but this is just much easier to write because you don't have to hassle with these 3 times 1 matrix. Okay, is it clear enough? Any question? Good. So these are the basics. I think this is the only thing you need from linear algebra for deep learning, actually, how to multiply vector by matrix. And that a matrix is a linear transformation. It has a meaning. Linear transformation has a meaning. Okay, so then we have the mathematical foundations here, which we'll need today. And let's move to supervised classification setup. So what are we trying to achieve today, actually? Was it binary classification of reviews? Right, okay. So we're gonna build a function around this. And we're gonna, so typically we restrict ourselves to search over specific families of functions. So something where we say, yeah, the function from the input to the output couldn't be anything. It could be something where we say, yeah, maybe just a linear function, right? Why not? So when we restrict ourselves to sort of like a class of functions, we're putting there some inductive bias. So we're saying, well, only certain solutions are important. Okay. So let's move to high dimensional linear functions now. And oh, this is a very awful slide. I'm sorry about it. But let's go through. So what will be our function? It will be from some input dimensions to some output dimensions. And we're gonna, oh, we've seen this before. So our linear function is already what we've seen before. It's a vector times a matrix plus another vector. Okay. Yeah, so this is our linear function. So we write it as fx, or here fx with the parameters very explicit here, like the w matrix and the b vector. Okay, so this is our linear function. It's basically multiplying a vector by some matrix, which is a projection, and then adding something here, some another vector. Okay, all good? Everybody's with me? Linear function, vector times matrix plus a vector. It's very simple. It's indeed a like very simple mapping, very simple function. And here, so okay, we call them, the x is the input, and the matrix w and b are the parameters. So we call them the parameters of this function. And here we have put the explicit parameters here, right? So we're saying, yeah, this is parameterized by v and b. Okay. So the output of this function will be something projected and a little bit shifted. And okay, back to the parameters, we denote them with this very ugly thing. So what is this ugly symbol? Anyone recognizes this very ugly symbol here? It's theta. Yeah, it's theta. It's a big, large theta in LaTeX. Okay, so this is theta. It's very fancy in machine learning, like parameters is theta, whatever is in there. So our theta here, our parameters are w and b. And now we want to, yes, you have a question.
What's the difference between the parameters within w and b?
What's the difference between the parameters w and b?
What's the difference between a parameter in b and a parameter in w?
What's the difference between w and b? Well, so they have different, well, they are all, both are parameters of the function of the linear transformation, only the w is a matrix and b is a vector. This is the only difference. That's the only difference. It's just parameters of our function.
Like there's no other meaning for a parameter.
I don't think so. I don't think so. So parameters means I have a parametric function. What could be another parametric function? Well, I don't know. Something which is not linear function. Okay, so Gaussian distribution. Who knows Gaussian distribution? So it's parameterized by mu and sigma. Like the mean and the standard deviation. These are parameters of the function, right? So, and then the function depends on these two parameters. If you write a Python function, you put parameters in there. There could be anything. One could be an array, and or it could be a string, whatever. So it's the same thing, okay? And the goal of learning is to find such values of w and b that our function is doing what it's supposed to do on a collection of input values. So these are the inputs, and these are the outputs. So basically, for each input, it should produce the expected output, right? So we want the function to take text, which is positive, and to spit out positive. That's what we want to do. And we're going to model this with this linear function, right? And we want to learn such a parameters of the function that the function is doing, or the prediction is doing what we want to do it. Is it clear enough so far, or anyone struggles with this formalization? Great. We're going to make it much easier in the next slide, because we're going to focus on binary classification. So here, the input will be still some high-dimensional vector, but the output will be a scalar. So it changes our function from the previous one, like this. W is not a matrix anymore, but it's just a vector. And this is what we had before again, like linear. So dot product was some offset here. Okay, so this will be our binary classification linear function for today's task. So, but okay, so for binary text classification, our input is in the form of natural language text. Where do you see natural language text here? I don't. I see X, and this is like a vector. It's kind of how. What should we do? Okay, well, this is one problem. The other problem is that the labels we are having, positive and negative, are two categories, but our y, our output of the function, is a scalar, right? So what shall we do about it? Well, this is simple. This task, we're just gonna say that we're gonna map these categories into 0 and 1. So we're gonna say maybe like negative will be 0 and positive will be associated with 1. This is our arbitrary decision. So it could be the way, other way around. Why 0 and 1? Why should we shoot 0 and 1? Any idea why is it so? Exactly. This is convenient. It's not the easiest way. It could be like -1 and +1, or 0 and 100, but 0 and 1 is just mathematically convenient. So it will be, it will play out easily then in the calculations. So now we have to talk about the first problem, right? I mean, how to take natural language text and plug it into this input, like vector. Oh, okay. So numerical representation of natural language text. It's gonna be a little challenging here. So we need to transform text into a fixed size vector of real numbers, right? So this is our setup. This is our function. Vector in, scalar out. So this is solved, but we need a vector in, which is this function. So we need this thing, but what we have is the text. For example, one of my favorite movies ever. Now here, see the typo here, so there's no white space. Jesus, people are terrible in writing. The Shawshank Redemption is a modern day classic, and a blah 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 blah, and another like 100 characters. So I mean, they have differing lengths just to begin with. Like one review is just 20 characters, another is like 50 pages long maybe. So we need to transfer it into these words. We need to transfer them into a vector. How shall we do that? So there is one thing we need to talk about, and we need to talk about what is a word. Right? What is a word? So it's a matter of debate among linguists. It's not always clear. But for us, so let's start with some very simplistic definition that words are sequences of letters separated by white space. Fair enough. So, but then this example like dog, comma, dog question mark, dot period, and dog parenthesis. These would be different words, right? If we just split them by white space. So yeah, maybe this is not like the best definition ever. So then let's do better. Words are separated by white space or punctuations. Yeah, this is much better. So we would solve this. And the process of splitting text into these words, it's called tokenization. So we split it into so-called tokens based on white spaces and punctuation. And the thing is, like in English, the job of the tokenizer is quite simple, right? So we have like words, white spaces, and punctuation, and you cut them into tokens and call it a day. So Hebrew and Arabic, anyone speaks Hebrew and Arabic here? Yeah, can you split the text by white space? Most of the time. Okay, so this is like so-so. Yeah, let's see. So who speaks Chinese here? Can you split the text by white spaces? Yeah, so I would say like 1% of the time it will work. Maybe. So why? Yeah, exactly. So in China, I don't speak Chinese, but I kind of believe what they're saying, that there's no white spaces in Chinese. So how can you split a word? Yes. Is it? Is it like one character corresponds to one word? No. Yeah. Yes, sometimes. Yeah. Oh yeah, it's complicated, right? Okay, so that's why. Okay, so now, okay, let's forget words and come to tokens. Okay, so this is complicated, right? Tokens. And then the symbols cat and capital C cat have the same meaning, but are they the same word? Well, it depends. Or something like New York, is it 2 words or 1? So we're going to distinguish between words and tokens. And the output of the tokenizer is then by definition token, and something which has the meaning, and you can find maybe in dictionary will be words. But keep in mind that we will use these terms word very loosely, and we will interchange with tokens, right? So kind of we ignore all these tiny little details from linguistics and say, it's word or token or tokens mostly. But the reality, the story is just hard, right? As we just saw. But anyway, we want to really tokenize Chinese text. We want to tokenize Arabic text and stuff like that. So let's start with it. So let's start. How can we? So the goal now, what's the problem again? We want to turn text into a vector. Okay. So we know what the words or tokens are. We can tokenize text. This is great. So let's start. Let's start building vocabulary. So we take a training data maybe or some other data, and we build a fixed-sized static vocabulary. And how can we do that? Maybe by tokenizing some training data, right? So you basically take your training data, which is 100,000 documents, you tokenize it, and then just take all words you found, put them into a set, and call it a vocabulary. Sounds good? Sounds good to me. I mean, this is how typically things have been done or are done. So the typical sizes of vocabularies are, roughly 20,000, 100,000 words. How many words are in a language? Like how many words are in, I don't know, English? Distinct words. 600,000. Yeah, I trust you. It could be like that. Yeah, it could be more. In like, depending on the word, what word is it a lemma or is it just with suffixes and things like that? If you tokenize training data, you kind of ignore all these nuances, and then typically you would pick like the most common words, like what are for the vocabulary, like most common words, 20 to 100,000 words, and then you basically maybe sort them, maybe not. So here are just alphabetically sorted, and this is a vocabulary of the most common 3,000 words in English, and each of them is associated with the index. Here we're using one indexing. So the first, at position 1, we have this word, position 2, the word, and so on. So this is our vocabulary. We train, we use it from a training corpus by tokenizing. Okay, any questions? So we need a tokenizer, and then we can build a vocabulary. And then once we have the vocabulary, we can take the document, and for each word in the document, we can look up a vector from this vocabulary, or build a vector from this vocabulary, and combine them together. So here's how it goes. It's called back of words. Let's forget about this formula first. Let's start with the example. So we have a sentence, a cat said. So we tokenize it into a, cat, and said. These are 3 tokens. And we have this vocabulary, 3,000 words. And there is A is at position 1, there's even cat at position 852, and maybe there's set at position somewhere, I don't know, somewhere 2,179 maybe. So now for the word cat, for the word A, the first word of the document, we're gonna look into the position of the vocabulary where the word is. So A is position 1, and we're gonna put A1 into this vector, and the rest will be zeros. So it's called one-hot encoding or one-hot vector, because there is just one position which is sort of hot, like on or 1, and the rest is called like zeros. I think it's coming from some electrical engineering, maybe the term. Anyway, so one-hot encoding. So then we take the second word, a cat, okay, and find where the cat is in the vocabulary. So it's at position 852, which means it will be all zeros, except for position 1 at 852. So there will be only 1. And the same will do for the set, which is somewhere at another position. So all zeros and just 1. Okay, so this is how we get one-hot encoding for each of the words. Any question? Yes.
D is 3,000?
Say again?
The D in the absolute value, is it 3,000?
Like the size?
D is 3,000.
Oh, no. The D is the length of the document. So this is document D. Okay, let me just come back to the formula here. So we are well, the formula will be clear on the next page. But here we are first looking at these vectors. So we're looking for each of the word of the document. We're iterating. So the I is iterating over each word. So here will be 1, 2, 3. And we're looking out for each of the word, the one-hot vector from the vocabulary. Does it answer a question? Okay, you have a question.
Why do we use one-hot encoding? Because like a word can only be one, so we can just like write in 0 ones.
I don't think I understood your question.
So like instead of writing 1 0, like 1 1 and 2,999 zeros, we can just write like log 3,000 like zeros and ones. Like just write it in zeros and ones.
So he's referring to like the characters, like put it into char, look it up, like a number, and then you have.
You can write it just a number. You would just write, okay. You would say A is 1. You would say, okay, so here I'm gonna use different color. Yes, this would be like 1. This would be like 8052, and this would be like 2179. This is what you propose. Okay, this is a good idea, but the problem is that you're putting this into one scale, which will make it somehow ordered or comparable. I mean, these are discrete things, so there is no their distance is always the same. There is no notion of similarity. While if you put them into just one scalar, you're imposing some sort of ordering of these words, or they're too close, they're closer in this dimension. But how do you know? You don't know. So you basically start with this one-hot encoding, right? So this wouldn't really work then in the models we're trying to do, because these are distinct categories. You have to kind of put them each into one dimension. Yes, we have a question.
So one of the important things here is that the distance is always the same.
Yes, yes.
Okay.
So the distance, okay, who knows Hamming distance? One, Hamming distance, okay, very few. So Hamming distance is basically how many, if you have these two, so how many bits are different, right? So what's the Hamming distance between these two words? 2, exactly. What's the Hamming distance between these two words? 2 again. What's the distance between these two words? 2. Right? So they have the same distance to each other, and there is no notion of similarity at all whatsoever. This is a feature and a bug at the same time. Feature because it's simple, bug because it won't work as we want, so we will find better solutions. But this is like the most basic thing. Yes? You just proceed as usual. You just have multiple words. I'll get to the full back of words in the next slide. Yes?
Talking about the order of words.
Oh, the order of words. This is interesting. Okay, let me go to the next slide, and then we'll talk about order of words. Because then we take the average back of words, which the formula was we're kind of summing up all the vectors. So here we say, okay, this would be like, so the sum will be 1, 0, 0, then will be 1 somewhere, 0, 0, then will be 1 somewhere, and all the zeros. This will be the sum of the 3 vectors, right? And we're just dividing by the number of tokens here, which is 3. So here, the size of the document is 3, which will gives us the final 1/3, very many zeros, 1/3, very many zeros, 1/3, very many zeros. This is the final thing. And there's 2 things we are discussing. One is the ordering of the words. So what will be the difference between a cat set or a set cat? This makes no sense, obviously, but what will be the difference in the final representation? None. Yes. So you basically, by this one-hot encoding or average back of words, we're just throwing everything into one bag and don't care which word comes after which one. Okay? Is it a good thing or a bad thing? It's a bad thing. Well, yes, I would say yes. I mean, it makes no sense linguistically. Empirically, it works really well as a feature for so many classification tasks. You will be surprised. Okay? It makes things so much easier because it's basically throwing everything into the bag. So then there was a question who asked like the repeating words. Yes. So if you had like a cat, set, then you would count. So this would be like the last word again. You would count it twice, and basically this will change to 1/4, 1/4, 1/4, and 1/2. Okay, good. Any question to this? Yes. You might. Okay, so New York question, which is interesting. If you consider in your vocabulary, if New York is 2 words, then you would have like 1 hot encoding for new and 1 hot vector for York. And obviously this will break so many things for the reason like you're throwing everything into one place and just there is no, yeah, it makes no sense. So maybe New York should be 1 token, maybe. And then you, if New York were 1 token, you would represent it as a 0, 0, 0, 0 position of New York is 1 and 0, 0, 0, 0 until the end of the vocabulary. Okay. Yes.
You have new as word, York as the word, and New York as the word. How does the
Yeah. I don't think you would have it like that. I don't think so because of the ambiguity. Like, why? So the idea is vocabulary is basically to have the lowest kind of, it should be like prefix. So if you go from left to right by the characters, you hit the end of the vocabulary of the token or the longest sequence of characters which corresponds to the word in the vocabulary. It should make sense like that. Okay, good. Yes. Yeah, absolutely. The method has problems with everything which has something to do with linguistics, like negations. Of course. I was happy. I was not happy. Well, not. How would you, like, you can make up an example where the ordering really makes a huge difference, obviously. Yeah. Negation is one of them. The movie was good. The movie was not good. You throw it into one and then, yeah, well, what's, yeah, not good or good. Yes. Second? Misspelled words. Well, misspelled words is like how you build your vocabulary. So yeah, so misspellings is like you have the same word twice in the vocabulary. Once is misspelled and one is correct. This is a trouble. You first, you second.
Not cringing at all. It was not. I was cringing all the time.
Yeah. Yeah. Okay. Yeah. That's it. That's the yeah. Good example. Exactly. Yes. Okay. You are second.
It's imaginable that there are tokens that won't be in the vector, so that we will leave out words that are not interesting.
Exactly. So
I didn't look it up.
okay, good. Good for you. Good for you. Don't look it up. Don't spoil it. So there's words in language that are words in language are unevenly distributed. There's a thing called Zipf's law, which somehow says like there's an exponential decay in the distribution of the common words. So there is a large sort of tail of this distribution of rare words. So most words are somehow at the beginning, they're mostly used, and there's just words that are rare. And there are a few kind of just used very rarely, but they're there. So this is the long tail of the distribution. Okay. So as I said before, when building the vocabulary, we use the most frequent words and all others represented by an sort of like unknown token. So we use UNK or maybe OOV, which is out of vocabulary. So here, our example of the most common 3,000 words, we would kind of extend the vocabulary with this extra token, UNK, would be maybe at the end or maybe at the beginning, doesn't matter, right? So we just say we have an unknown token in the vocabulary. And now it means if you're trying to do one-hot encoding and you find a word, so you tokenize a text and there's a word which is not in your vocabulary, you're going to say, well, it's an unknown word. So you're going to use the vector for the unknown. Okay, does it make sense? Yes. Mm-hmm. Right, yeah, yes. Maybe, yes.
Those very small numbers like the characters A, B, and C, because if you take the longest match, then those A and B would just be
yes. Good. No. I mean, it's really cool because it makes you think like how to solve it, and this is exactly what people are doing. Yeah, this is really cool. Yeah, I like it. Yeah. So if you don't, yeah. So, okay, exactly. So in the unknown, back to the problem, and then we'll get to the solution. The problem is like in machine translation, So you translate from a sequence of words into another sequence of word. And if your input sequence of word, you find like unknown word, how do you translate it? Like so tell me, what's your name? Luis. Okay, what's your surname? Müller. Müller. Sorry, Müller. 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 Okay, Müller. Very nice, because this word is not in my dictionary. I know Müller, but it's not a match. So it's Müller, and I would say, oh, good morning, Mr. Müller. I want to translate it to. Sorry?
Wouldn't be the first time.
Yeah, exactly. And I want to translate it from English to German. But I'm parsing the input sentence. Good afternoon, Mr. Müller. I would take it, good afternoon, Mr. Unknown, because the word doesn't exist in my vocabulary. Okay, so what I'm gonna do? I'm gonna translate into schönen guten Nachmittag, Herr Un. Yeah, that's bad. So what I can do is like to take these unknown words and just copy paste to the output. It works most of the time for names, places, and stuff like that. But maybe there's a better way. Okay, so let's go into subword units. All right, so we're gonna use the thing called byte-pair encoding. And there's a procedure and how to build your vocabulary from the smallest units ever. And I guess it goes really along the lines you proposed. So let's take the words in the corpus and split into characters. And we can take the original space with a special space character, right? So we basically split everything into characters. And this will be our initial vocabulary V. So we have vocabulary only by characters, no words. Then we'll find the most frequent pair of characters and merge it and put it to the vocabulary. So we'll find what's the most common pair of characters and merge it and take these bigram of characters and add it to the vocabulary. And then we're going to repeat this for a very many number of times. We're going to be merging the most common things after always updating the vocabulary. And each of these steps will increase the vocabulary by one thing and beyond the original inventory of single characters. So we're building from subword units and basically growing the words. I'll show you an example and it will become much clearer how it works. When this is done over large corpora, and maybe then with multiple languages as well, so maybe all the Wikipedia languages, the byte-pair encoding actually will help you prevent auto-vocabulary or OOV quite a lot. It's very helpful for machine translation. Why is it so? So let me show an example. On a toy corpus. So we have a toy corpus. It was like this fat cat with the head is in the cave of the thin bed. And we split it by characters, and this is the white space, right? We use this underscore for white spaces. So this is the first step. And now we put all the characters to our vocabulary. So D, H, I, S, and so on. Then now we find the most common, most frequent bigram of characters, which is the TH. So, right? TH here, 1, 2, 3, 4, 5, 6. And we're going to merge them into a single token. So we add TH to the vocabulary. And now, using this new one, we're going to, we merge them and then we basically repeat the same thing. So what is now the most frequent bigram? You see here, we have TH as one unit, one token. Okay. So we're going to find, maybe A and T is 4 times here. So the most common thing is A and T. And we're going to merge them again into a single token and put them into the vocabulary. So here, you see, we merge AT here, AT here, AT here, and there's one more, which I can't find. What? Yeah, thanks. 4 times. And let's go again. Okay, so here in the next one, so this is the previous example. Now, the most frequent bigram is now THE. So which is here and here and here, and we're gonna merge them and add this to the vocabulary. And okay, this is the next step. So we have the word already. You see, we are basically coming to very frequent words based from single characters. So we're building the vocabulary really from scratch. So after this process, we have in the vocabulary all these characters, right, up until here, then these bigrams, but then actual words starting to emerge because they're very common. Yes, you have a question. Exactly. When you, okay, I didn't put it there. When you hit your size of the byte-pair encoding, so you would say, I want typically 50,000 maybe, or 100,000. Similarly to the vocabulary, but now you have all the subword units in there. Okay, another question? Yes.
Do we also remove tokens? For example, the T is not text anymore.
No, no, you keep everything there because it happened as a bigram in the training data. So you keep everything and you just grow to words which are very common, and you end up with words. Any other questions? You had a question. Uh-huh. Exactly, yes. Exactly. Maybe, yes. Yeah. You say like, well, I want a BPE by 50,000 maybe units, and then you start basically this process. First, second, third. Yes, I mean this is like, yeah, you don't care after you finish this vocabulary, this byte-pair subword to vocabulary, you don't need a text. It's just for learning. You had a question?
Tokenization for that whole sentences that are very common would be tokenized.
It might be even like whole sentences, but it won't be the case empirically. It could be like you grow that longer over tokens that you will end up with maybe like longer sentences, but it's not the case actually. So it's not really the case. Maybe because you just tokenized before and ignore the white space. I'm not sure really. That's correct. Yeah, that's correct. I think byte-pair. I'm not sure. I have to double check. I don't know whether byte-pair needs pre-tokenized text. Yeah. Sorry, you had somewhere in the back, and then you. Inefficient? Why? What do you mean by a lot of space? You mean like the back of words is inefficient because you have like large vectors?
Yeah.
Yeah, that's correct. But what is large? Yeah. So sure. I mean, 100,000 dimensions input vector. How large is the computer vision image pixels MNIST? How large is the vector? 7080 something times 7080 something. Since 16,000 bits, or not bits, 16,000 pixels. And it's small. So it's relative. So times 3, yeah, okay, all the RBG. You had a question? Yes, but yeah, that's fine. Maybe you don't need it. I mean, yeah, you don't actually need it. Yes, you have a question.
The thing is, not like very frequent words don't really have meaning like stop words.
Mm-hmm.
So what like those frequent words, the stop words, they're like their own dimension. But like
yes,
actually more important, probably more important words like whatever get split up into like two dimensions.
Right. Yes, it's possible that you split up words that are kind of that happen that are often you might end ending up splitting them. That's the risk. That's true. But you can make it bigger. Let me show you an example. Okay, like a real. So here is the byte-pair example trained on. So this is like 49,500 steps of BPE. And this is how you split a sentence using BPE. The relationship between Obama and here the word was Netanyahu, which wasn't apparently in the training data for BPE, but it learned how to split it even like a little bit like it makes a morphological sense after syllables, and then the rest are just words and punctuation, which is in the vocabulary again.
so that even not nearly that frequent, but kind of frequent words
might be split up.
still get their own dimension.
Yes, yes. But it would be the same thing if you take 50,000 words, like just tokenized words and sort them, you would be surprised what's in there. Like very weird words, because how many words you use per day? Like different words, 200, 300. So 50,000 is a lot. Actually, like 50,000 words in a language, if you know, like learning 50,000 different words in a language is quite a lot. It's a huge, like long tail, very rare words. But the advantage of that is that you split words that kind of you can translate then easily. And if it's yeah. Any other question? Yes, you.
So if I understand this correctly, it's this is more about like tokenization, and
yes,
still use one-hot encoding.
Yes, yeah. Well, because we are talking about like tokens, and you said, yeah, well, everything is token is split by words. No, actually, I mean, you need to really, if you do something later on with we'll see models like BERT and transformers that use sort of input tokens, but these are subword units. And it's important to to take it into account, because you can use these subword units as the input for the linear function as well. You can use just very simple unknown words as well. So this is just a different flavor how to transfer text, which is a stream of characters, into distinct units, which are tokens. Okay. Another one here is a variant of byte-pair encoding is SentencePiece coding. SentencePiece encoding, SentencePiece tokenizer, and it works like it takes actually the white space also into account, which would maybe help us with the New York thing. I guess SentencePiece would kind of take a New York as one token, very likely. So it adds here the underscore for the white space, and then builds the the same iterative process, and then the splitting would be basically non-destructive. So it's like lossless tokenization, because here you can reproduce this back to the text. Here there was some tokenization before, and it's not maybe one-to-one, because between these two words, well, there was probably a white space, but here, yeah, who knows? It shouldn't be any white space. With SentencePiece, you have the white space very explicitly here, so it's a different variant. It's a very popular one. So if there is tokenization, you should know SentencePiece tokenization. Okay. Any other question to tokenization? Now we kind of take a tangent a little bit, but I think it's really important to know that it's just if you cut into words. Yes. How do you do exactly the tokenization? If you have the SentencePiece vocabulary, for example, you start looking into the longest sequence of characters which are in your SentencePiece. And in the worst case, what would be like worst case? If you don't have the word in your SentencePiece vocabulary, what would be the worst case of splitting the text? Single characters, exactly, because we have the single characters, we started with the single characters. So even like the super weird words, you can tokenize into characters. It will be hard time then for the models to learn something meaningful, but who cares? So there is nothing lost.
Right there is SentencePiece example. Could you do a live example of how we do this? With the
like this up here.
Yeah.
This is typical to this. This is how is byte-pair encoding implemented in the original paper. So you would add these two special characters. These are the word splits. So when you split a word, you add these two ampersands here at the end, because Netanyahu is one word, and you split it into 3 tokens, and you signal here by this that you're splitting basically the word into subword units.
And is this related to the last part?
SentencePiece works differently, because it doesn't have these ugly ampersand characters. It just takes even like white space at the same time, just put special characters. There is no tokenization before in SentencePiece, and it's learning basically just from the characters. For the byte pair, we had to tokenize it first by white space. So there are subtle differences. I would suggest you to read this paper, like this one. There's very clear example how this works and what's the difference. Okay, you have a question.
Yeah, so the two options are do this like from scratch, or just take the white spaces and everything consider a token everything that's separated by white spaces left and right. If I don't see the advantage of this alternative thing.
Yeah, okay, so you don't see why this should be better than something else like the token.
Yeah.
Because here you don't have the unknown problem. You don't have like you don't have unknown, you don't have OOV. Everything will be represented.
But I'm gonna take a lot of known words and, for example, the word world. I don't want to split it into space WORLD.
Okay.
So I'm gonna lose more than win, I think.
Yeah, well, in the simple example of this one-hot encoding, there's no really, I don't think there's like super really advantage of using SentencePiece and SentencePiece tokens. That I'm on their side. But then later on for machine translation, for example, and using transformers, the input will be much better because there is some composition of these words which are splitted, and you can translate. You can learn something about translation of these pieces as well, even though it's not in your training vocabulary. That's the point. Like, it's shaky explanation now, but believe me, this is helpful for machine translation quite a lot. And then it is being adopted to everything. Like SentencePiece is now the tokenization for everything you do with transformers, for a reason. Okay. Good. So tokenization, vocabulary. It's covered. Everybody's with me. Good. So what are you trying to do? Okay, we had to transform text into fixed size vector of real numbers. So we made it. We have now the back of words tokenized. The tokens could be really like words, white space, or it could be subword units. Fine. And the dimension is the size of the vocabulary, right? So some people consider it huge, like 50,000 vector. But this is fine. Okay, so I'm thinking what to do next. Because I don't think we'll cover everything I tried to cover today, but let me give a shot, like in next 15 minutes. So the goal, okay, binary text classification. So movies, right? We want to. What do we have? We have this function. Okay, we know how to convert text into a vector. This is great. We have this linear function. What was that? It was this. This is our linear function. So we're gonna multiply the input by some matrix and something else. And the output will be a scalar, which is 0 or 1, right? So everybody's with me on that? Okay, cool. This is what we wanted. So we have this linear function. And now, coming back to lecture 2, we're gonna pack everything together. And what we say like was the only thing every function we're working with when we want to try to minimize something is that we need the derivatives. Like every function has to be differentiable. So what is derivatives of this function, this linear function, with respect to the parameters? So the parameters are w and b. And this is super simple, actually. These are beautiful derivatives. So the partial derivative of this function with respect to any of the parameters is just why is it so? Because the partial derivatives of this with respect to w1, you treat this x1 as constant, so this will be x1 and the rest will be constant, which is 0. Okay? Does it make sense how we do these derivatives of this linear function? If not, look it up from last time or just look up how to do the differential derivatives of multivariate functions, and you'll find it easy. The same with what's derivatives with respect to b. So everything else is 0 and b is will be just 1. Okay, so we can differentiate this function. This is great. It will be helpful later. I mean, maybe not clear now why, but we have a function which is a linear function, a mapping from a vector of back of words into a number, and we can differentiate it. Okay, cool. Now the point is, so we have this function, right? So this is our function, linear function mapping, and the range of the function is unbounded. What does it mean? Well, what comes out could be anything from infinity to minus infinity, right? I mean, this could be anything. But the problem is, each example label was either 0 or 1. We said, I mean, this was our design decision. We said like, oh, let's put it negative will be 0 and positive will be 1. So there's just 1 and 0. The point is, well, how to reconcile this? How to make this somehow compatible? Because we want our function to predict something which is either 0 or 1, but now it's predicting something from between minus infinity to plus infinity. So it's unbounded. What can we do about it? Okay, you first, you second.
You can define some thresholds. You can decide under this certain threshold value it's a 0.
Oh, you can say it's threshold, and if the threshold is over, then you would say it's 1, it's a 0. It's actually a very clever idea. You can maybe take, like, if it's positive, it will be 1. If it's negative, it will be 0. Okay, yeah, that's possible. And I think it's actually, if you do it like that, you'll end up with a perceptron. So yeah, it's very clever. And same? Okay, good. Yeah, you can do some thresholding functions saying, what's the problem with the thresholding function? There's no problem actually. It's fine.
You have to find the value.
Yeah, define the threshold. Yes. Okay. Yeah. But if you can say, well, it's going to be in 0, and what's positive will be 1, and what's negative will be 0. Why not? Any other idea how to transform this something which outputs minus infinity plus infinity to something which is going to be 0 or 1? You first, you second.
Yeah, you could add some also threshold, but you could add some area of uncertainty.
Oh, you can add area. Okay, good. Area of uncertainty. How would you do that?
Maybe randomize one area so that we get some noise within data.
I wouldn't go into noise of data. I wouldn't. Oops. Sorry. I wouldn't go there. I mean, randomization of data. It's nice if you do differential privacy. So if you want to randomize data, come to my group, and we can talk about randomization. But I wouldn't go there. You had an idea. Softmax. Okay. So softmax already. Will it work here? For a binary output for just one single scalar? Softmax is something else. Well, it will work. Yes, I guess it will work. 1 over, it will do something, but maybe not what we really want exactly. Anyway, sorry, you, and then I'll go over. Yes.
Saturation function.
Saturation function. Okay, what is it? Oh, yeah. So you would somehow make a function which does this mapping by itself. Yeah, okay, exactly. So a very popular function here is the logistic function, or sigmoid function, which takes a real number and outputs a real number, and takes any real number as input and produces exactly values between 0 and 1. This is a saturation function. This is what you want. So we're mapping through the sigmoid function everything into this interval. Okay. There's other functions, but this one is like the mainstream sigmoid, like mapping everything into between 0 and 1. And it has this form, and I really want you to know this. Okay. Sigmoid. You should know sigmoid. If you say, like, I had deep learning for NLP, and ask what's a sigmoid? I'm not really sure the formula. I can look it up. No. You have to know this. Okay. So what is interesting on this function is that it has a meaning, and I'll come to the meaning later on. But maybe the first thing, we put a sigmoid there. Okay, so we had this output of this function, and then we put it through the sigmoid. So what do we have to know about a sigmoid function as well? If we want to plug it into some minimization, what do we need of the sigmoid? What do we need to know? We need to know the derivative of this function, exactly. Yeah. So a little bit of homework, derivatives, blah, blah, blah. We end up with something which is very nice. Actually, the derivative of the sigmoid, it's the value of the sigmoid times 1 minus the value of the sigmoid. So the computation will be like easy because you know the value already, and there is no extra, exponentiation on whatever. So this is very nice computation. It's very convenient. Okay, so we have this sigmoid, and we're gonna plug everything together. Okay, any question to the sigmoid function? So yeah, anyone? No, it's clear. I mean, we're taking everything and plug it between 1 and 0, 0 and 1. Okay, and it's nicely centered around 0, and it has this beautiful derivative. which means at any point we have derivatives. So here, the more to the right you go, the derivatives will be 0, and here the derivatives will be 0, and here the derivative will be roughly 1, and so on. So it's nicely differentiable.
Is it computing the sigmoid function itself is difficult? Like,
you need just one exponentiation. So how do you compute exponentiation? What is x of x? How do you compute this?
e to the power of x.
It's e to the power x, but how do you compute e to the power x?
Approximation.
Yes, which is?
Series.
Yes, it's a series. Okay, so we're gonna have sum of.
I don't remember the exact.
Yeah, okay. I guess it's 1 plus x over n from n is 0 to infinity. Is it somebody can look it up? Is it correct? No.
Without
No, wait a second. This will be a limit. N goes to infinity.
Yeah.
This is correct. And there's a sum and it's different. It's okay, the sum will be what is it? K over K to n over n factorial, right? Yeah. Okay. Yeah, so you can do either one of those. Right. So it won't be hard. Well, okay. So this is easy, and we have this as well. Yes, you have a question. Why? Okay, the question is why did I put t here? Right? What is t? So I put t here just not to confuse with anything else, because it's just a function which takes real and outputs real. The actual input will be, thank you for the bridge, will be the output of our linear function. Okay? Yes, thank you. This is great. It's really like, it's a dialogue. Exactly. So here, let's put it into computational graph. So what we had so far, this was our linear function. This vector input times vector plus an offset, and now we plug it into the sigmoid, right? So this will be the parameter of the input of the sigmoid. And we can build it as this computational graph, which looks beautiful. And if this is the same, actually, this is a very same computational graph we had in the last lecture. You basically, each node is a function and has some arguments. So this is a function of the linear, this is the linear function, and the inputs are the vector x, the vector of the parameters, and here the offset, the b, coming here, and the output of that goes through the sigmoid, and coming out is this y hat. Why is it the hat? Because this is the prediction. This is not a true label. True label is just the y. This is y hat, so it's not the same thing. It's like the prediction, right? Oh, this is cool. So we have this computational graph. I'll finish in 3 minutes. Okay. Now, what do we need to do? Okay, so we have this output of the sigmoid, and we are doing the binary classification. So what's coming out of the sigmoid is values between 0 and 1. So how do you know like what is going to be 0 or what is going to be 1? Yeah, we're going to use a threshold. So somebody said here threshold as well. I mean, we have now threshold as well for this sigmoid. So we're going to say what's coming out of here. If it's bigger than 0.5, it's going to be 1. And if it's smaller than 0.5, it's going to be 0. If it's exactly 0.5, we throw a coin, something like that. No, well, it's arbitrary decision. It could be like greater or equal. So why is it so? Okay, well, let's come back to this sigmoid function, right? So here, yeah, it makes sense. Like this is an odd function, and now just in the middle, we say, oh, here's the cut. So if it's larger than 0.5, we're going to say it's 1, and it's 0 otherwise, right? It makes a lot of sense. But now there's a very cool thing about a sigmoid, because it's not, if we had like a thresholding function, which would be like, oh, I can use colors. Maybe. Here would be, and then a step, and here. So this would be like 1 and 0. Yeah, this is threshold as well. So if it's bigger than Oh, it makes no sense. I'm sorry. No. Let me just roll back. I'll cut it off from the video. No. So this is nice because it has also the value of this y hat as a natural interpretation. And it's saying us the probability of prediction is equal to 1 given the input x. So again, the sigmoid output here is the probability that y is 1 given x. Does it make sense? If I'm coming back to this slide, if I'm here, it's telling me, yeah, it's like 80% probability that I'm close to 1, and 20% probability that I'm close to 0. So it's like natural interpretation is a conditional probability. So the output is like, oh, given the feature vector x, the probability of the output being 1 is this output. So you can use it for decision, make a cut after 0.5, or having also like confidence of the model a little bit, right? So if the value is something like 0.55, the model is not really sure. If it outputs like 0.99, then the model kind of knows.
Chance that the function will be 0, that the value of the function will be 0, and then you have to type, or
the value will be 0. So the value of the sigmoid will be 0. Oh, this, okay, so it's coming 0 coming in. So the value coming in will be 0 here. And you end up with 0.5. Yeah, that's possible. Yeah, exactly. I mean, you can make like arbitrary choice. You say either, yeah, it's so it could be greater or equal to 0.5, then it's 1, or it could be 0.5. It's gonna be 0. It's up to you. Or you say like, I can't tell. You can play around with the value. Okay. Any other question? Okay, good. So a small recap. I mean, there's more, but we'll do that next lecture. So let me just recapitulate what we had before. Whoops. And there's just a few slides, but we shouldn't rush. So tokenization is tricky. Language is tricky as well. I mean, language is tricky and tokenization is tricky because what's a word and how do you define a vocabulary and so on, but it's important. We learned the simplest representation as a back of word features. So this is something you should kind of take away with you. Back of word features. This is like the most simple thing of representing language, throwing into a bag and making vector out of it. And we learned that we can do binary classification as a linear function of words and the sigmoid over that. And this is something we learn next time. Any other questions so far? Good. Thanks a lot. See you in a week.